Okay, this is the next section of the syllabus on the part on nerves, and this one is 4.1.2 part F, and this is interpreting graphs of the voltage changes taking place during the generation and transmission of an action potential. So this follows on from the previous tutorial, which showed you how an action potential works to move an electrical stimulus, an electrical impulse along an axon from one end to the other. And this graph represents the voltage changes that will be typical of that action potential moving through each part of the axon. So what you need to be able to do with this graph is to understand the different sections of it. You need to be able to quite possibly to reproduce it, and certainly to add labels and explain what's going on at each part. So on the left hand side, the potential difference, so this is across the membrane of the neuron. It's measured in millivolts, and along the bottom, time is measured in milliseconds. Over on the right hand side over here are a number of still shots from the action potential animation that you saw in the last tutorial, and we're going to use these as we talk about the different stages of the graph. So at the start, which is represented by the black, this black line at the start over here, this is where the nerve is at rest. So this is what we call the resting potential. You notice that this graph begins and ends at resting potential, so it's similar to the animation you saw the other day with action potential, showing how the action potential works. So with this one, we're starting at minus 70 millivolts, and this is our resting potential. And notice at the end of this process, we go back and reach the same point. So we also go back to minus 70 millivolts. So if you remember, at resting potential, we have a large number of positive sodium ions outside, and a certain proportion of potassium, also positive ions, on the inside of the membrane. There is a greater number of these positive charges, these positive ions on the outside compared to the inside. So we can say that the inside is relatively negative. It isn't negative, but relative to the outside, it is negative. So it's and the value of that typically is about minus 70 millivolts if you measure the potential difference between the two areas. So what we need to do next is we're going to see what happens as the action potential moves through this section of the axon. And you may remember that the next section is called depolarization. So in depolarization, just looking at the animation still over here to begin with, the sodium channel, the voltage gated sodium channel opens, and the sodium ions move down their concentration gradient from outside the neuron to inside the neuron, and that's down their electrochemical gradient. So that's represented by this upward curve on the trace, the red line here. So we'll just label that as well. And so that is depolarization. So typically in an exam, you may be asked to say what each part of the, the wrong spelling, there we are, no, what each part of the graph represents. So this is depolarization, and important to remember therefore that with depolarization also what happens in there. So this is sodium ions moving in across the membrane and down into the axon of the nerve. This happens for a little while until the basically until the sodium has run out, as it were, and they've moved all down through the sodium channel and into the inside of the neuron. Typically, this changes the membrane potential to a value of around about plus 30. It can be different for different neurons. You may see it as plus 40 in your textbook, but around about that value. So what that means now at this stage is once the all of these green sodium ions have moved through, then we have a high concentration of positive ions on the inside of the neuron, and it's much higher, it's much more positive relative to the outside. So we end up now with a positive potential difference across the membrane. Another thing to mention before we continue is you, again in the exam, may be asked to highlight on here the point at which a stimulus is applied. So remember, at this while the trace is flatlining at the bottom down here, then the nerve is at rest. But as soon as that trace starts to go up, then that's the point at which the stimulus was applied. Whatever that stimulus may have been, it may have been a change in light, change in sound, a change in temperature, but you need to be able to identify where the stimulus was applied on that graph. So you see then the depolarization stage begins, and that implies that the sodium channels have opened and the sodium ions are rushing in. What you may also be expected to do is to label what's happening to the channels at different stages. So for instance, at the top here, at this stage, we have some action with the sodium channels. So now the sodium channels will now be closing at the end of depolarization, and the potassium channels will then open, and that starts the next stage of the process. So next stage, if we just drag down and see the next still of the animation, so the first part was depolarization, and the next stage when the potassium ions are rushing out, so that's indicated over here on this diagram. So the potassium ions are moving outwards to the outside of the nerve cell, outside of the axon, down their electrochemical gradient, and this is repolarization, so the opposite, if you like, of depolarization. So that was depolarization on this side and repolarization on this side. This continues until more and more potassium ions move out down their electrochemical gradient. And you may notice down here in this purple section at the bottom of the graph, we actually go underneath the value of -70. We go below resting potential. And that's because of the huge outflux, if you like, of the huge movement out of the potassium ions. So we have this area here that we call an undershoot. So we're, if you like, shooting under what the resting value is. So many potassium ions have rushed out that we go to a more negative value than what we would normally have at rest. So this is this section labeled in purple here. You may remember from the animation, I'm just going to drag this down, that what happens next is that this section of the axon that we're talking about must then return itself to resting potential, ready to receive the next action potential that's coming along. So this is where the sodium-potassium pump on the right-hand side here works to move 3 sodium ions out and 2 potassium ions in, so in that 3:2 ratio. And that's a pump, so it's an active process, and that will restore the resting potential. So that will be this last black line that you can see here. But as you can see, it takes a little bit of time for the nerve, once the potassiums have all rushed out and finished their movement, it takes a bit of time to get back to its resting state. And this little undershoot over here, the whole time period, also has a name, and I'm just going to label that here, and that's called the refractory period. And that has some significance to do with the direction of that the impulses and the action potentials move along an axon, and also giving the axon time to recover before the new action potential can begin. So there's this recovery time, and it's only a couple of milliseconds, but it's enough just to reset the neuron, so then it's ready to receive the next action potential. So you can't continuously fire action potentials. There's this very short time delay that we call the refractory period, which I'll just circle here. So it's the whole of this area down here is the refractory period. So make sure you understand the difference between that and the undershoot. The undershoot is just the difference. So we drop down to about a value of about -80 millivolts with the undershoot. So I'll just maybe add that onto here as well. So undershoot goes to -80 millivolts. Okay, just a couple of other things before we finish. This green dashed line along the middle at about -50 millivolts, but again, it could be different for different neurons, so you may see it differently in your books. So that's this green dashed line. What that's called is the threshold potential. So I'll just type that here underneath. And threshold potential is a value of potential difference that must be reached if in order for a full action potential to take place. So if you can imagine, nerves are stimulated all the time, and some stimuli are strong and some stimuli are not strong. And so what happens sometimes, if the stimulus isn't strong enough, and I'll just do this in a different color. So the black line in the end reached the threshold potential, and because it did, it then induced a full action potential in this part of the nerve. But what may happen if the stimulus isn't strong enough is that we have some influx of sodium ions and it goes up, 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 but it's not quite enough, so it kind of dies away again and returns to resting potential. And that may happen again next time. I'll just do this one in red. So here's the next one, and it goes up, 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 doesn't reach threshold potential, so then just falls back down to resting potential again. So these are not full action potentials as we've seen here with this original red line. And what the green and the red line that I've just added on here are what we call are what we call failed initiations. So they haven't quite reached the level that they need to in order to generate a full action potential. So if that's the case, then at that part of the neuron, that nervous message would then stop, and that impulse wouldn't continue until the end. I think that's about it. So lots of labels, lots of new words around the outside. Try to remember the values: -70, around about +30 or 40, depolarization, repolarization, the refractory period, the time for rest, and then also the undershoot. Just one final thing to label, and I'm just going to add another arrow, and that's the space above the threshold up to the top of the full action potential. Again, another new name, I'm afraid, and this is called the overshoot. Oh, another funky arrow. Let me just undo that, and we'll go to this one. So that distance there represents the overshoot. So we have overshoot and undershoot. And I think that is it.